Okay. Hi, everyone. So yeah, I'm going to talk. This is going to be a rather technical talk about how to do follow-up observations when you have a small or mid uh, radius field of view of your pointing telescope. So I've done this work together with Halim, Fabian, and Mathieu that are in the room. Does it pass? Okay. So which are the science cases for these algorithms? So we've been talking for many years about gravitational waves interferometers being able to pinpoint their source better, but we see even with the presentation yesterday by Marika that this is not necessarily going to be the case for all our events. So we need to be ready for this. I put here other examples, not only gravitational waves, but this is also the case for GRBs detected by Fermi GBM and also neutrinos. Here I included the cascade events, but maybe one day we'll have the track as well. So to be able to follow these events, we need observation strategies, and this is the topic of this talk. So a bit of history on how this started. First of all, we had the gravitational wave case. So everybody started to develop these algorithms to follow these events because it was the only way to do it. So this was about 2016. And that's what we did for the HESS telescopes to be ready for observing run 2. We were ready to follow up the gravitational wave 170817. And then after that, we generalized the codes for GRBs. We put the code not only in the HESS alerter, but also in the transient handler of LST, which is the large size telescope of CTA. Then going back to the codes, we improved them so that we could also, we improved them and we created a Python package so that it would be easier to install and could be used for any poorly localized event and also by any multi-wavelength ground-based facility. Since recently, these codes are also implemented in their own API, and they are embedded in Astro-COLIBRI. Okay, so some of the actually scheduled follow-ups with these codes. We have here the example of that I mentioned before, gravitational wave 170817. So this was the tiling derived by tilepy and done by HESS. So we have here the first pointing, second pointing, and third pointing, and we pinpointed. So you see the events. So the real localization of the source is over here. So we covered it. This was very nice, but we kept doing gravitational wave follow-up observation. So here you see an example. This is only some of them. Actually, these are the public ones, but we are also doing GRBs. Okay, so going to the architecture. So this is now very modular, kind of flexible code that can handle multi-observatory, multi-telescope, and multi-wavelength observations. So it's very simple. You see, we have some set of inputs. So your favorite telescope config, the sky map, and the time. Then the core functions are organized in 3 levels. So you have the observation scheduling, which is going to do the parsing and is going to take decisions. Then we obtain the tiles. So this one is in charge of obtaining these. And for that, it's using the low-level functions that concern visibility, probability computation, and other optimizations. So with all these, you can already get a schedule for the night, but we have some extra tools that I will describe later. Okay, so first, the observation constraints. So now the code supports any type of observation constraint, so daytime, moon time, and also dark time. Here we see an example of moon time. So we have the moon over here. We need to have the distance between the moon and all the coordinates of the sky map to be able to know which ones are too near to the moon and which ones are accessible for us. We also take the moon phase and other parameters. And then regarding the observation constraints, well, We also take into account the atmosphere effects. So this is an example. So this is an optimization on the zenith angle, actually. So we for example, for gamma ray telescopes, we're gonna aim to have observations at the lowest energy threshold possible. So this is an example of HESS CT5 telescope. So you see that going from a 0 zenith angle observations to 40 to 60, we are losing orders of magnitude of energy threshold of the observation that we are going to take. So this is also part of the code. There's some weighting done so that observations closer to these zenith angles are selected instead of those being over here. Okay, now moving to the probability. So we have these probability density sky maps. And what we do is to use the center of the pixels as a grid. So you see here we have the grid of pointings. We use two maps, so one high resolution and one low resolution, so that it goes faster. Because if we were using the high resolution, we would have too many dots. This changes depending on the observatories that we are using. But for me, telescopes, for example, this is a nice way to speed up things. So then you will have all these possibilities and you will select the highest, the one covering the highest probability. We are also masking observed regions and in this way, and we can go from this to this. Okay, then we have 3D algorithms. So those are the ones that take this probability density sky map and then are kind of convoluted with the galaxy distribution, so galaxy catalog, so the local distribution of galaxies. The most common example where this is used is in gravitational wave follow-ups using the GLADE Plus catalog. There's two possibilities. So we are either going to use the coordinates of the galaxy as coordinates of the grid, so as our grid. This is going to create a very very kind of non-isotropic grid, but we can also use the center of the pixel. So we've checked both methods, and they have very similar performances. So here you see the one using the center of the pixel. So that's why these are more organized. This is 170817. So you would have this low resolution map, and then that you use as a grid. And then this one is the one covering the cluster of galaxies, and then you select this pointing. Okay, so just a note on how we use the galaxy catalog in tilepy if you're going to use Astro-COLIBRI. So we take GLADE Plus catalog, which has many objects, actually 23 million, and then we cut it to fit our needs. So we don't need all these objects. We just need the ones that are in the zone that gravitational waves from binary neutron star mergers can be detected. So we are doing a cut that is already very not super conservative, so around 500 megaparsec. We end up with 4 million of galaxies, and we are not so conservative with this because to decide which algorithm to use, we are gonna use this consideration. So we take the luminosity distance of the event, and then we take 2 standard deviations from there. This information is in the gravitational wave schema. And then we say we do 2D or 3D. We also account for the galactic plane region that is kind of empty in these catalogs. Okay, other functionalities that are part of this scheduling code is that we allow to use a physically motivated weighting. So this is an approach that is outlined in this paper. We call it mangrove because that's how they call it as well. That's the name they gave it. And by now, we are weighting by the galaxy mass, but we could also weight by the BNS merger rate that now is included in the GLADE Plus catalog. We do second round. What does that mean? This means that if you have a probability density profile that is very steep. So you have a lot of probability in the center, not so much in the outer parts. You may say, I just want to follow the center part. I don't care about these small ridges over here. So you would use this second round. So you would focus on the central part of your uncertainty region. Obviously, we need to account for previous observations because we have updates both for gravitational waves, but also GRBs. So we have this way of taking just an input file and then subtracting. So we mask that part and we start the scheduling. And then this last feature of ranking the observations, this is something very useful when you are actually scheduling this for shifters, because for instance, I put here this example. So due to the evolution of the field of view that is accessible at a given time, this is evolving during the night, right? So the beginning of the night, you will have 0, 1, 2, 3, 4, 5. Actually, 5 is not there, so only until 4. So you see 0, 1, 2 is over here, so covering a better region, 3 and 4. And this is the beginning of the night, because actually the accessible region of the sky is going like this, no? This zenith angle cut. So it's moving in this direction. But if you are at the middle of the night, actually you don't want to follow this guy over here. You want to follow the one here. So the priority would be start with 2, then 3, then 1, then 0, then 4. So we provide this as well. Okay, now I want to show you this multi-telescope coverage. So imagine that you have 4 telescopes, say 4 LSTs, that want to tile independently an alert. So this would be what LST1 could do. We put 20 minutes of exposure, 2.3 radius of the field of view, and a zenith cut of 70. So this is for the first, this is for the second, this is for the third, and this is for the fourth. And all together, they do this nice coverage of the region. So comparing to what we could do if we had only one, we go from 1 hour, 40 minutes of follow-up to 6 hours, 20 minutes if we had only one telescope observing. So this is for the multi-telescope coverage, but we also check the multi-observatory coverage. So this is something interesting when you have telescopes all around the globe, or if you have, in this case, MAGIC and LST in La Palma and HES in Namibia. So each of them have different, they are different in the field of view they have, in the exposure of the runs they take, and in the zenith cuts, let's say the accessible sky. We did this scheduling, and we have observations from this time to this time in MAGIC and LST, and HES would start later. So you see that HES can cover parts of the sky that are complementary to what the others cover. So here you see in black HES, LST is in blue, and MAGIC is in green. So in this way, we can cover a large region of the sky that it wouldn't be reachable only by one site. Okay, then other examples of multi-wavelength coverage with another field of view, because I was mostly focusing on mid-size field of view, basically gamma ray ACT. So here you see this way smaller. So this follow-up was during the day. Imagine with a radio telescope of this region of the sky that is very looks like thin stuff, elongated. So the visibility of all of them, it's very similar. We see that we start observations at midday until 9, more or less, and we can cover a large region. Just 2 examples of, again, small field of view, but this one galaxy targeted, and this other one also galaxy targeted. This is 170817 with the visibility of Namibia. So let's say atom telescope or whatever optical telescope you have there. And we cover the real, the host galaxy in the first point in here. Okay, so this was all for the demo of the different cases. Where can you find tilepy? So we have a demo tilepy in GitHub that needs to be updated with the version 1.0. You can also find it in its API. So that looks like here, and then you can run with a command that looks like this ugly thing, but where you see you can modify the fits map and the time and other parameters. And also you have the user interface via Astro-COLIBRI. I'm going to try to do a demo. Let's see if everything works. And then just last slide, what do we have in our to-do list? So basically keep up with future changes in the community. So we're probably going to add we're going to add everything that has a helpix sky map. It's very easy. We just need to plug it and it just works. So neutrino GRBs, in our work to-do list, we also have it to make it faster. The speed of the code depends a lot on the case. So I cannot give you the estimate can be very broad, but for example, for these things that I showed is on the order of tens of seconds. We want to do it more modular, so it's easier to implement more science cases and allow for contributions from the community. So this is all. Now I'm going to show you the demo via Astro-COLIBRI. Fingers crossed it works. Yeah, okay. Okay, so you have it here. And then you see the gravitational wave sky map over here, and you go to science mode, and then you go to schedule. And this was pre-computed, and it's very fast because it's already there. And you see the tiles over here. So the coverage in percentage of probability, the coordinates, the best window, and then my browser doesn't allow me to continue, but I guess you have the best window and that's all. So this one, I think we put JEG or something. Wait. Oops, the other one. Jylink, yeah, Jylink. Yeah, Jylink. Yeah, we could do that. So here we have the 3 tiles and they are over here. So they appear here. And I think you can see where is the visibility? Daily, yeah, sorry. So daily plots. Yeah, okay. So you could do that with all of the tiles. And the third one. Yeah. So that's how it works. And then this is the API I was mentioning. So you have here the parameters, description, and then a usage example and the associated JSON. And that's all.